working? Where'd you go blank? Oh, there it goes. Okay. Welcome back to Monday. Let's get started. Hoping to finish up chapter 32 today, and then we have a worksheet for chapter 32 for AC power and voltages, and then hopefully we'll start chapter 32, which is on electromagnetic wave. Is the chapter before you have to take a midterm. And I think the midterm was scheduled on midterm 3. It's on May 8th, right? So it's 2 Mondays from now. Okay. And that covers chapter 29 through 32. Okay. The 4 chapters we're going through right now. Before we get started, is there any questions or concern about the schedule? You okay? Okay. So last time we ended up with this thing called an RC circuit, right? Where you put a capacitor and a resistor in series with each other, and you either look at the output of the resistor if you want a high pass filter, or you look at the output from the capacitor, or by output I mean the voltage between across the capacitor or across the resistor, right? So I'm going to do a little, because I think the example I went through last week was not very clear. So I just want to go through that as maybe a simpler one today. But one of the interesting thing about when you put the resistor and a capacitor circuit components together in an AC circuit, you have this not weird, but like you have this behavior where, right, the resistor voltage, meaning the voltage across the resistor, right, it starts off at 0, but then goes up as you go to higher and higher frequency. Okay, and then the capacitor is the opposite, where it starts off at basically whatever your EMF voltage is, right? Whatever your AC, so if it's 120 volts, then it starts off at 120. But then as you increase the frequency, it goes down, right? Has this interesting behavior where two things are doing opposite things with each other as a function of the frequency, okay? So if you were doing this at 60 hertz, it'll have a behavior at 60 hertz, but if you go to higher frequency, it changes, right? And we can actually calculate this behavior by calculating these capital V's and capital VC's, right? These are the peak voltage, meaning, right, these are the amplitude of these oscillations, right? Okay, and I just want to go through this example maybe a little more clearly this time, where let's say we have a RC filtering circuit like this, where we have a some AC source, and we're going to take the output at across the capacitor, okay? So this is what we're going to be measuring with our ohm meter or whatever, right? Your little meter, okay? And this is to showcase how a low-pass filter can be used to remove background noise if we set up the filter with a certain resistance and a certain capacitance, okay? In this case, we're going to set it up with a resistance of 100 ohms, right? So this R value is 100 ohm. Okay, and this capacitor value is 1 microfarad. Okay, so these are pretty typical numbers that you will find in a lab for these components. Okay, so let's say my voice, gets amplified and converted into an electrical signal, just like what my Bluetooth headset is doing for me. Okay, and let's say this voltage, this signal is going to be like something that's 10 volts, and then somehow the stuff got cut off. The OneNote decided to adjust the width for me. Okay, anyway, let's not try to fix that. So I'm just going to write this at the end here, right? 400 hertz times time. So that's the function, right, of my little voltage source, right? That's what I'm inputting here, okay? So therefore, what you can do is just kind of do it like a matching situation, right? Where now we can see that, well, EMF naught, right, is 10 volts, right, just by matching what's in front of the cosine function. Okay, and then the frequency, right, we have omega, right, it's going to be equal to 2 pi times 400 hertz. Okay, So 400 hertz is typically, I think it's an okay voice frequency for a male voice. Okay, if I multiply those together, right, the angular frequency is going to be 2.512 times 10 to the 3, and this will have this units of 1/second. We can put the radian in if we want, but usually we try not to do that because it'll just kind of be confusing to think about it in terms of radians. But it is kind of like an oscillation that's going around in a circle. Okay. And the question is that, well, what is the peak voltage across the capacitor? Okay. Meaning, right, we want to calculate this number, right? Okay. VC. Okay. Okay. What is VC equals to, right? Because that's the peak, right? That's not, it's basically what the amplitude of that oscillation is, okay? Right, so to calculate that, right, we used our little equation up here, right? Actually, there's a simpler one that we found yesterday where if we just multiply this through the denominator is EMF naught times R times omega times C, all of that square plus 1, and if you want to just do that algebra step, you can show that that's actually true. Okay, so therefore we can just put in the EMF naught, right, square root R omega C, all of that gets squared plus 1. Okay, and then since we know what EMF naught is, we know what R is, we know what C is, right, we know what omega is, right, all of that can get added together. I'm going to pick a big square root. So R is 100 ohm, right? Let's just write these values down also. And then C is 1 microfarad, and then omega is this, right? Okay, so 100 times omega, omega is this 2.512 times 10 to the 3, times 1 microfarad, which is 1 to the negative 6, right? And all of that gets squared, and then you have to add a 1 to it, okay? And I'm missing a parentheses, okay? So the voltage across the peak voltage across the capacitor is 9.7 volts, okay? Okay. And the important thing is that, right, this is approximately 10 volts, right? So you didn't lose that much voltage by passing this voice signal through a low pass filter, okay? So this is known as a low pass filter because we're going to let low frequency sound, low as in 400 hertz, pass through the circuit itself, okay? Let's see what happens if we have a high frequency noise, right? Let's say some noise in this room, right? It's like 4 megahertz, right? So it's probably some sort of electronic noise that you don't want to listen to, okay? What is the peak voltage across the capacitor for this particular frequency, okay? So I'm going to do the same calculation here, right? The only difference, right? Let's just plug in the 10 volts here, right? I didn't change the circuit at all, right? So it's still 100 ohm, right? But omega is very different because now we have a different frequency. Let me cross this out, just write it up here. Right? The frequency is actually 4 megahertz instead of 400 hertz, okay? So omega is actually 6.28, which is 2 pi, times 4 million, 4 times 10 to the 6, right? Let's see what that number is. 4e6, right? This is 2.512 times 10 to the 7, right? This will have units of 1 over seconds also, okay? So if I plug that in here instead, 2.512, okay? Do you guys want to venture a guess whether or not I'm going to get approximately 10 volts from this, or I'm going to get something else? If it's a low pass filter and I'm sending in a high frequency source into it, should I also get about 9 points? Should I expect about 9.7, or should I expect something less? Something less, right? Because we're trying to filter out this high frequency signal, right? And then the capacitor is 10 to the 9 minus 6, 1 microfarad. All of that gets square, and then you have to add 1 to it, of course, okay? And let's see what happens when I plug those numbers in instead. Oops. If I can get out here. So the voltage I get out is actually 0.003, well, 398, so basically 0.0040 volt. Okay? So notice that when I pass a low frequency signal into my low pass filter, I retain most of the low frequency stuff. But when I put in a high frequency, meaning 400 megahertz instead of 400 hertz, so much faster, right? I only get 0.04 volt back. Okay, so basically all of the high frequency signal gets suppressed. Does that make sense? Okay, and that's the idea for these low pass filter. Okay, and it's used in every one of your devices, so that's why I want to make sure that this example is clear. Okay, any questions? And if you did this with a high pass filter, the opposite would happen, where the high frequency signal will stay at like 9.7 volts, but then the low frequency signal will get reduced to like 0.00 something volt. Okay. Okay. You want this number to be low. Oops. And you want this number to be basically whatever the EMF source is. Okay. Okay. All right. Now let's move on to our next component, which is inductor. So last week and the week before, we got introduced to inductor. Okay. And I'm actually going to tell you what the answer is, right? Because the thing we did with resistor and capacitor was that we had this thing called the capacitor reactance, right? This capital XC, right? And we basically was able to figure out that, well, that's just the same thing as omega times C, right? 1 over omega C, right? Right. So this number has some frequency dependence on it, right? That's why that plot looks like that. Okay. And then resistor is the boring thing where, you know, resistive reactance, right? For a resistor is just R, right? Because we don't have a phase difference between that one. I'll tell you what the answer is for inductor, and we're going to see that in a second. Inductor is going to behave similarly, where instead of 1 over omega C, it's going to behave as just omega times L, whatever the inductance value is. Okay? Okay. Just a reminder how inductance work, right? Just imagine you have a little solenoid, right? And all these solenoids will make a little bit of an inductance, where if you have a current passing through it, right, we can quantify this quantity called inductance by knowing how much the voltage will drop when there's a current that is changing that goes across inductor. Okay, so the thing that makes an inductor drop in voltage is change in current, not current itself, not charges, but the change in current. Okay, so it's a little wonky. Okay, so the voltage across an inductor, right, is the inductance multiplied by the derivative of the current. Okay, the time derivative of the current. Okay, the faster the current changes, the bigger that voltage drop across the inductor is. Okay, so just as what we did before, we're going to start off with just a simple circuit with just one AC source. This is just our AC source, right? We have our one component, and let's just see how it behaves. Okay, so we have since we only have one component, okay, we found that basically whatever the EMF is as a function of time is going to be equal to the voltage drop across that inductor as a function of time, right? That's just from using Kirchhoff's law, right? So I can even start it here. You start off at 0. Well, you start off at this point. When you go across it, you gain some EMF around amount of voltage. When you go back over here, you lose some voltage drop across that inductor, and now you're at the same place, right? And then you can solve this for each other, and then you can find that they are equal to each other in this circuit, right? Because it's a very simple circuit, okay? Right. In this case, right, we also have the equation that the voltage drop across an inductor is proportional to the inductance times the time derivative of the current, right? How fast is the current changing? So therefore, we can plug this in over here, right, and equate the two sides, okay? So E as a function of t is this EMF naught cosine of omega t, right, just as usual. And that's going to be equal to L di dt, right? And this is across the inductor, right? So this is the equation that we're going to be dealing with, okay? This turns into something called a differential equation. So those of you who have had differential equation can solve this pretty easily. But I'm just going to show you how to do it. You don't have to do it yourself. It involves just some integrals, right? Where if I solve this equation up here for di, right, I get di up here, the right-hand side turns out to be basically, oops, the right-hand side turns out to be whatever the voltage across that inductor is divided by the inductance times this cosine of omega t thing times the derivative of dt, okay? And the way you solve these type of things is you basically just integrate both sides, okay, to get rid of the differentials, right? Okay, okay. When you integrate both sides, what happens is that it turns this cosine function into a sine function, right? Integral of cosine is the sine, okay? The other thing that's important is that this omega pops out as a denominator. Remember when you take a derivative of cosine, right? A factor, a multiplicative factor of omega comes out. But if you do the integral, you have to divide that, right? It's the same, it's just doing the inverse action of it, inverse function of it, okay? So that's why this omega comes out in the denominator, okay? Just the same trick as we did before with when we deal with capacitors. We know that a sine function is basically the same thing as a cosine function, but shifted earlier by pi over 2, okay? This is a positive sine function, right? So we shift early, okay? But if, remember when we did the capacitor, we have negative sign, that's why we shifted later, okay? So that's why this sign is different between capacitors and inductor, okay? They have opposite phase shift, and so that's going to be the important point, okay? What we're going to do is then, well, we have this blob of stuff here, okay? And what's it going to call that blob of stuff? Well, this has to have units of current, right? Because whatever is in front of that cosine has to have units of ampere, right? So we're just going to call that the current across that inductor, okay? Sorry, the peak current across that inductor, okay? And so from here you can find that, well, that peak current has to be equal to whatever the peak voltage is divided by omega L, okay? And now you're starting to see where this omega L comes from, okay? If you solve this equation for V sub L, right, like up here, where you're going to see that the voltage across that inductor, sorry, the peak voltage across that inductor is going to be the peak current across that inductor times omega L, right? And this is why, right, we're going to call this omega L the inductive reactance, okay? It's called the inductive reactance, okay? Same thing as the capacitive reactance before, but now it's for inductor instead, so it has a different dependence, right? It's proportional to omega as opposed to 1 over omega, right? It's also proportional to L, okay? So comparing this to the other reactants, right? So we have Ohm's, the original Ohm's law, right? That tells you that V equals IR, right? We have the capacitor version of Ohm's law, right? Where V equals to IXC, but then IXC is this omega, sorry, this is an I up here. This is omega C, right? Okay. So the inductor version of Ohm's law, right, is just the current times whatever this is, and we're going to call that XL instead, okay? So all of these components follow the same generalized law, but just be a little careful, right? The capacitor and the inductor, they both have a frequency dependence, okay? So how resistive they are depends on the frequency that of your voltage source, okay? And this actually gives you like very interesting behavior, okay? What we're going to do is once again we're going to do these little graphs where we're going to plot the current across the inductor, right? So it follows this purple graph, right? Because it's just a sine function, right? Where the voltage across that that inductor follows the cosine graph, okay? And this is where a lot of people get confused. It's like, this looks as if, right, the current, sorry, the voltage is actually, looks like it's behind the current, right? Because the green is actually kind of like, following behind there, right? But the way you should interpret this graph is that, right, at t equals to 0, right, you get the maximum voltage, right? Right? So TVL is max, right? But at t equal to 0, right, your current is actually 0, okay? It's actually, so you should think about this in terms of kind of like looking at it vertically as opposed to horizontally, because that always confuses students and they're going to get this stuff backward, okay? So when you look at this vertically instead, this way, right, the voltage gets to the maximum first, right, and then the current reaches the maximum at 1/4 of the period later. Does that make sense? Okay, so therefore, the voltage is actually 90 degrees ahead of the current, okay, in reaching that maximum point. Okay, so I know I'm going to kind of this detail thing, but this is going to confuse you if you ever have to build circuits and become electrical engineering, stuff like that. Okay, or you're going to take the next class in electronics and physics. Okay. Okay, so when you draw the phasor diagram, okay, let's say you draw the current in this direction, you're going to have to draw the voltage at 90 degrees ahead of the current, okay? So that's how we draw these little phasor diagram, okay? So the thing you want to if you want to memorize these things, okay, that inductor voltage leads ahead of the current, okay? Okay. For capacitor, it's backward. The voltage lags behind the current. Okay. Unfortunately, leads and lags starts with the same letter, so you don't actually get a good acronym out of it. So, but the way to think about it is that inductor leads, okay, and capacitors lags. Okay. Okay. All right. So let's do an example. Sorry, before we do the example, any questions about this lead lag situation? Okay. So let's do an example. So this will hopefully be a nice illustration. Okay. So we have a 25 microhenry. So that's the unit for inductor. Okay. So it's an SI unit. So as long as you know it's an SI unit, you can do computation with it and not have to worry about unit conversion, right? And it's used on a circuit that oscillates 100 kilohertz. So it's, it's kind of a medium frequency. Okay, not too high, not too low. The current going through the inductor reaches its peak value of 20 milliamp. Okay, so let's write this down, right? When they say peak value, that means it's giving you this capital IL thing, right? Those are the peak value. Those are the amplitude of the oscillations, right? So this is 20 milliamp. Okay, and in fact, they also gave us the frequency. The frequency is 100 kilohertz. And then the inductor value is 25 microhenry, and micro is 10 to the minus 6. Okay. It reaches its peak value, 20 milliamp, at t equals to 5 microseconds. Okay. And the question is asking you, what is the peak inductor voltage, and when does it occur closest to 5 microseconds? Okay. I think we can probably get this peak inductor value without doing a lot of work. But to understand what's going on, to figure out the part B of this problem, it's very useful to make a little drawing. Okay. So what I'm going to do, I'm going to do a little drawing as a function of time. Okay. What I'm going to do is do the same thing as what the book did. I'm trying to remember what their color coding is, right? So in green, I'm going to plot voltage as a function of time, and then in purple, I'm going to plot current as a function of time. Okay. Okay. All right. So this little statement here is stating that at 5 microsecond, right, the current is at its peak value, right? So this is where this happens. So I'm going to mark a point up here, 5 microseconds, right? And I know, right, the current is at a peak, right, at this point. So it has to be up here somewhere, okay? Right, something like this, okay? And I know what this amplitude is, right? It's given to me, okay? So how is the voltage going to look? What will be the green graph look like? Should I draw the green graph since voltage on an inductor leads the current, right? Should I draw this wave like this ahead of the inductor? Did I do that right? No, right? Because this makes it look like the wave is the green wave is ahead of the purple wave, right? But what you're interested in is actually the value on the vertical axis, right? So if you draw the wave like this, right, right, the voltage reaches its maximum value before the current, right? So that's what leading means, okay? Okay, so just be really careful about drawing these graphs, okay? Because otherwise it will just get you the wrong answer, okay? And oops, I probably just kind of drew it like this also, okay? Right? So part B of the problem is trying to figure out what this time is, okay? Right? But let's just try and figure out part A of the problem. So I already typed out the concept. The first concept is basically just to find the peak voltage using this generalized Ohm's law. Not everyone calls it that, but you can, it looks like Ohm's law all the time, right? Okay. For the inductor, in order to find the peak voltage, because, right, the generalized Ohm's law for an inductor, right, is just L times omega L. Oops, omega I times omega L, right? Where this omega L is this inductive reactance, okay? So we know what the peak current is, that's given to us. We have to convert our frequency to omega, right? Omega is just 2 pi times the frequency. Therefore, it's just going to be 6.28 times 10 to the, so that's 1, 2, and that's 3, so that's 5, right? So that's what omega is going to be. And then the inductor value is also given to us, so let's write all that down. So the current is 20 milliamp. The peak current is 20 milliamp. Ooh, I should actually not write milli. I should write 10 to the minus 3, right? Okay. The frequency is 6.28 times 10 to the, there's a 5 up here. 5, that's 1 over seconds. Okay. The inductance is, wrote it, 25 microhenry, so that's 10 to the minus 6 Henry, okay? This is an SI unit, this is an SI unit, this is an SI unit, so whatever the answer is, it's going to come out in voltage, right? So I multiply all these numbers together with my calculator. 20 times 10 to the minus 3 times 6.28, 10 to the 5, positive 5, okay, 2.5 times 10 to the minus 6, okay? If I multiply all this together, I get 0.314, and that's going to have units of voltage. Okay? So that's part A of the problem, right? So I didn't actually need to do this drawing to figure that out, right? I could have just applied this Ohm's law, right? But part B, right, I'm going to have to figure out that, well, if the peak value for the current happened at 5 microseconds, I expect the peak voltage, right, to occur a little bit before 5 microseconds, right? Okay. In fact, in terms of the angles, right, how much earlier should it be in terms of either radians or degrees? 90 degrees, right? And 90 degrees on a cosine wave is 1/4 of a period, right? Okay. Right? Because if you go over 2 pi, that's 1 period, right? So if you go pi over 2, that's actually, so 90 degrees is pi over 2, so that's 1/4 of a period, right? Okay, so we know that the peak value for the voltage is going to occur 1/4 of the period before. So, but how long is this period? Okay, well, the period of an oscillation is 1 over the frequency. Here we go with chapter, whenever we covered this, right? Chapter 15, right? So we know the frequency is 10 to the 5 hertz, right? So therefore, the period is actually 10 to the minus 5, right? Just putting this upstairs and negating the exponent. And this will be have units, since hertz is 1 over seconds, right? Denominator over denominator gives you the numerator. So the period is actually 10 to the minus 5 seconds. 1/4 of a period, right? I'm going to rewrite this as 10 microseconds, because micro is 10 to the minus 6, okay? So 1/4 of this is 2.5 microseconds. So we expect that the peak of the voltage occurs 2.5 microseconds before 5. Therefore, it actually occurs at 2 microseconds, 2.5 microseconds, right? Right. T for the VL peak equals to 2.5 microsecond, okay? Not 7.5, right? If I drew that green wave in the wrong order, right, I would have thought it's actually 7.5 instead, okay? Okay. But always, just remember that whatever the voltage is on a inductor is going to happen before the current, okay, whatever the peak is, okay? Yeah, Lydia? Right, because we know that the difference between the the current and the inductor, sorry, the current and the voltage is 90 degrees or pi over 2 apart, right? And one period of a sine or cosine function has a period of 2 pi, okay? So 1/4 of 2 pi, sorry, 90 degrees is, or let's, I'm mixing pi's and radians, right? Sorry, pi's and angles, okay? So let's just talk about it in terms of degrees, right? So we know that the current and voltage is 90 degrees apart, okay? In fact, the voltage is 90 degrees ahead, okay? And one period of a sine wave is 360 degrees, right? Or 2 pi, okay? So 90 degrees is basically 1/4 of a period on our little cosine functions, okay? And that's why it's going to be 1/4 the amount of period that's going to be shifted by, okay? Right. So you're basically converting these angular quantities to temporal quantities, okay? Okay, right? Because one period is 10 microseconds, and therefore, right, a quarter of a period, which is how long it takes for it to shift by 90 degrees, right, is 2.5 microseconds, okay? Okay, and don't get this same number confused. This is actually answered by taking 5 microseconds, subtracting 2.5 microsecond. That's why it's equal to 2.5 microseconds, okay? Okay. It's not that I just calculated the period, the 1/4 of the period and plugged in the answer. It's because I know that this point is 5 microsecond, and I have to shift it back by minus 2.5 microsecond. And I ended up at exactly 2.5 microsecond, right? Yeah. Oh?
They say peak of the voltage or peak of current because it's alternating. It could also mean the minimum, right?
Yeah, you could also, well, when they say peak, they always say the highest positive value. If they say the trough, that's when you get the minimum. But you can do this calculation using trough or peak. It doesn't matter, right? Okay. But typically, people like to use peak because it's easy to see and it's positive numbers. Okay. All right. I got another 20 minutes, maybe even less, 15 minutes. Okay. So the next section is going to be the most complicated circuit we're going to have to deal with in this class. And I gave you guys like a couple of homework questions just for you to practice on it. But I'm going to say that I'm not going to ask a question on this on the exam, okay? Because to examine this closely, you probably have to spend an entire week just doing derivation on this, okay? But I'm going to tell you kind of like conceptually how this works. And I think a couple of you guys asked me, like, how do you build a resonating, what's called a bandpass filter or a resonator? I don't know if someone who asked. I don't remember who asked that, right? And this is basically how these work, because, right? So a lot of times the application is that instead of filtering for low frequency or high frequency, you may want to just pick out one particular frequency of signal or sound or whatever you want, right? So this is something that's plotting the frequency, right? And let's say, you're just measuring a bunch of stuff, but you are interested in this one particular frequency. You denote it FR for resonance. You just want to listen to this one frequency, okay? So for example, on your car radio, like this may be 91.4 megahertz, and that will allow you to tune your radio to that one particular frequency, so you only listen to this one particular radio station as opposed to all the radio stations at the same time, right? Which would not make any sense, okay? And that's how the way you make this is using these things called RLC circuit, where we're combining our resistor, our inductor, and a capacitor all in one go, right? We got three things going on in the same time, okay? So I'm going to kind of walk through conceptually how you would do this, okay? So you're going to do the same steps as what we did with the RC circuit, right? We're going to do a phasor diagram where, there's no units on these axes, right? What we're going to do is we're going to put the current in one direction. So that's kind of our reference. The reason we're picking current is that all of these stuff is in series with each other, right? There's only one current, right? Right? So we're going to use that as a reference, okay? Remember that the voltage across the resistor is in phase with the current, okay? Meaning, if you have the current going this way, the voltage across the resistor is in the same direction, right? So all of these are rotating around like this, right? I don't have three arms, unfortunately. Maybe I can use my legs, right? They're going to be rotating around in this circle, okay? But the thing we just learned is that the voltage across an inductor leads the current, right? It's ahead of the current. So therefore, it's actually the first arrow ahead, okay? And then the voltage across a capacitor lags behind the current. So it's actually negative 90 degrees down here. So that's why it's behind, okay? So this brings up an interesting thing, right? Where before what we did, it was just, if we want to figure out the voltage of the resistor and the inductor, we just did this, right? Where we'll have a little triangle we have to add using Pythagorean theorem, right? In this case, right, we have a more complicated situation because the voltage across the capacitor and the voltage across the inductor are pointing in opposite direction to each other. When we have vectors like that, what do we do? We cancel, well, you subtract them. And if their magnitude is the same, they do cancel out, okay? Okay. So what we need to do is that instead of calculating the vector for the inductor and the resistor by himself, you actually have to calculate the vector for L minus the capacitor, the inductor minus the capacitor, right? So you take this little piece and you subtract it, so this makes this vector here a little bit shorter, okay? And what you end up with is the length on each side is the length of the peak value for the inductor minus the capacitor, this square, right? This whole thing squared, I'm getting right up there, plus VR square, the peak voltage across the resistor square, that gets you the EMF square, right? And that's how you add these vectors together, okay? And it just turns out to be this long equation down here where the EMF naught square is equal to the resistor voltage square plus these two subtracted with each other first, then square, okay? All right, does it make sense? I have to subtract them first, right? Because, right, these two vectors are pointing opposite direction to each other, right? So the resultant vector will be shorter, right? Okay. Right. And then if we replace our little generalized Ohm's law, then we figure out that, well, this is just going to be current times XL minus XC, and you factor out the current, and you can solve for the current, so you don't have to write this down. This is all in the textbook, right? Where when you solve this equation for current, you end up with this interesting equation on the right-hand side here, where the current is proportional to the amplitude of the AC source. That makes sense, just like our previous equation. But then the denominator is more complicated. It has 3 different terms, technically more than 3 terms, right? You get this R squared, and then you get this omega L minus 1 over omega C all squared, okay? Okay. The interesting thing happened when we make this number basically 0, okay? How can we make this number basically 0, right? If we make omega L basically equal to omega C, right? If these two numbers, omega L is equal to 1 over omega C, right? Let's just plug this in here, right? So the current become E naught R squared, right? Instead of omega L, I'm going to write omega C instead, right? 1 over omega C. Oops, I can't write omega, right? All squared, right? This subtract themselves, of course, is going to give you 0, right? So the idea of this is that if you make omega L the same thing as omega C, you basically make the denominator as small as possible, right? Because anything that's not 0 here is going to be squared, right? Even if it's -5, right, it's going to get squared and it becomes a positive, right? It'll make the denominator bigger, right? To make the current as big as possible, you want omega L to be the same thing as omega C. Sorry, 1 over omega C, okay? And this condition is known as the resonance, okay? And this is how we pick out that radio station, 91.4 megahertz, whatever it is, right? Okay? This condition, right, makes it so that, well, if you solve this equation for omega, right, you get omega squared on this side, right, and then you get 1 over LC on this side. You square root both sides. You get that the resonant frequency for your RLC circuit is actually going to be 1 over L square root LC, okay? So if you want to figure out how to tune your radio, right, what your radio is tuned to, you just figure out the inductor value, you multiply it by the capacitor value, you square root that whole thing, and then 1 over that, the reciprocal, then you actually get the frequency that the particular circuit is going to be resonating at, okay? Okay. And I'll just show you a quick graph of what this looks like, right? So if you have multiple different values for resistors for your RLC circuit, if you have a small resistor, right, it makes the resonance much bigger. The reason for that is because of this formula up here, right? You still have this R square on the bottom, right? So even at resonance, right, you will still have to divide by the resistor value, okay? The smaller the resistor value, the bigger the resonance is going to be, okay? Okay, so at resistor value equals to 8, you have this nice big peak, so you're picking up your radio signal very well. But as you increase the resistor value, what happens is that this peak gets lower and lower and lower. Therefore, you're not resonating with that particular frequency as much. Okay, this is plotted as a function of omega naught, right? Where omega naught is 1 over square root of LC. Okay, right. So whatever that number is, right? Let's say you're tuned to 91.5 megahertz, to tune your radio station, right? That's where that is, okay? If you double that frequency, then you're not going to be at the resonance, right? So you're not going to see the signal as much, okay? Okay, I probably won't have time to go through the next section. Oh, there's a couple of interesting examples in the textbook where a lot of it is just kind of like knowing this equation and plugging in the right numbers, okay? So I'm not going to go through those, but I want to get you through a conceptual example where this is how basically all those RFIDs that you see on the doors here, how they work, and also on your credit card when you do that tap to pay thing. So how does it know, who you are and what your credit card number is, okay? So this credit card has a little chip. Well, this is actually not that. This is the what do they call? It's called something different. But inside the credit card, a lot of credit cards has like these wireless, tap to pay thing. It's actually a little antenna inside your card, okay? And these antennas are made of RLC circuit, the resistor, inductor, capacitor circuits that we maybe not know that much, but hopefully you will get to know at least conceptually how they work, okay? And an RFID reader, just like that little green thing right there, right? What it does, it needs power, so it has some sort of voltage source, okay? And it has some resistor, some capacitor, and an inductor in it, okay? This R here is the resistance of the antenna. It's just so to dampen the energy out, so you don't like break the thing when you run it at the resonance too much. Okay, so this is actually what's inside that green box, where it's actually have a frequency that's changing all the time. It's just kind of going up from 13 megahertz to 40 megahertz. Okay, and when you bring out your little ID card, let's say your student ID, if you ever, right, inside here is also a little circuit like this. Okay, where it's an R, a C, and an inductor, and also has a little chip on there that's programmed so that it responds to a particular frequency. Okay, and this is called an what is it called? An RF integrated circuit, and it's programmed so that when it senses things in a particular frequency, it either opens and closes a switch. Okay, so when it closes the switch, right, it connects this circuit together. When this circuit gets connected together, it will sense the magnetic field that's coming out of here, because the inductor here, right, what it's actually producing is just a bunch of magnetic field, right, and then it's going into here, right, okay. And the thing we learned from last chapter is that when you run a magnetic field through a loop, what will happen is that it will actually create a current in this loop, right? That's what's power this little chip here, okay? If that thing is connected, then it actually creates a self-generated and induced magnetic field. Remember this, that if you have a magnetic field that's increasing this way, right, it's gonna generate a magnetic field going back out here. So that's how the two actually communicate with each other. So when you put your card next to, I'm not gonna do that because that requires the police to come if I put it inside, right? If I put it next to each other, right, the magnetic field from there creates a little loop of current going inside my card, and the loop in my current in my card using Lenz's law that you guys learned about last week, right, creates a magnetic field that the sensor now can detect, and therefore, right, by oscillating the switch on and off, on and off, on and off. So when you have, those of you who are computer science, when you have things that are just on and off, those are just digital information, right? So you're just gonna get ones and 0, 1, 0, 1, 0, 1, 0. So, that information, right, will probably maybe show your student ID number and stuff like that. And that allows you to, to send the device the information and say, oh, well, yeah, I'm allowed to be in this room, so unlock the door, or pay for your groceries and whatever. Okay, so that's how these little RFID things work. Basically, it's just an RLC circuit on both sides that are communicating with each other with magnetic fields. Okay, so that's all I have for today. We're gonna finish up the chapter tomorrow and do a worksheet on it too.